thanks, Marta, for the nice introduction. And I wish, first of all, to thank the organizer for having invited here. So it's really a pleasure to present to this community these quite brand new results that we did in my group. So I appreciate to be here, really. So today we'll talk about something that is, to my mind, is a different perspective. So on what people are accustomed to. So people are typically accustomed to use the Josephson circuits for the realization of both quantum circuits like superconducting qubits, as well as more classical circuits, let's say like magnetometers, photon detectors, so forth, so on. But I mean, now I will try to convince you that one can use Josephson circuits in order to implement a completely different kind of objects. That is, I mean, that are thermoelectric systems. So the idea is to exploit Josephson circuits in order to realize power generation at cryogenic temperatures, as well as energy management. Okay, so in the sense to open possibly a new era for thermoelectric quantum materials and thermoelectric quantum system for power generation and energy management in a fully quantum technology environment. So the outline, so I will just start with some basic introduction to thermoelectricity, okay, from textbooks. And then I will show how it's possible to achieve thermoelectricity in superconducting Josephson tunnel junctions, okay? Then I will go on showing which is the experimental evidence of thermoelectricity in Josephson junction, and which are the main relevant figures of merit for this kind of system, and how is possible to implement at that point using this strong thermoelectric response of superconducting tunnel junctions, Josephson bipolar quantum heat engines and volatile memory cells as well. Then I will try to give a very brief introduction on more general Josephson thermoelectric quantum machines, so possible applications that we envision. And then I will try to summarize with the conclusion. So, let's start with some very basic concept of thermoelectricity. So what is thermoelectricity? Thermoelectricity dates back to the very beginning, I would say, of experimental physics, I would say 2 centuries, more or less, in parallel to thermodynamics. So as its ability, in some sense, is something, I would say, old school, okay? I'm an old school guy, so I like this kind of old problems with a new vision, okay? So thermoelectricity is the ability of a material to convert a temperature gradient in an electric signal and vice versa, okay? So the most well-known effect in thermoelectricity are, first of all, the Seebeck effect. What is the Seebeck effect? The Seebeck effect is a manifestation of a voltage which builds between 2 points of conductor kept at different temperatures, okay? And then there is a Peltier effect. So that refers to the energy transfer that can be heating or cooling between 2 conductors, metal or semiconductors in general, due to current flow. And in general, what is known, I would say, is that thermoelectric effects are based on the difference between the average energy of the conduction electrons or holes and the Fermi energy. So in the general, I would say, knowledge of scientists is that you can achieve a proper thermoelectric response if your system is sufficiently electron-hole asymmetric. So you need to start with the electron-hole asymmetry in the system. So this will provide you some thermoelectric response. So this is why people so far has been concentrating in finding and changing suitable methods in order to control the electron-hole symmetry in, let's say, in electronic systems. So to use N-type and P-type superconductors, so forth, so on. So what I am introducing to you is that we want to show a completely different approach in order to realize nonlinear thermoelectricity. So go beyond the linear response regime. So this is just, so in thermoelectricity, this is just a cartoon that probably all of you knows. I mean, it's just in the textbook. So we are, for instance, there is a lot of research in thermoelectric materials for power generation nowadays, which is focused on semiconductors. So we have a junction made, a PN junction with an n-type PN superconductor. I mean, as you're saying, the Seebeck effect refers to the power generation. So you have so these two elements, P and n-type, with like a heat sinks. Here we provide a heat source from the other part, and then this will lead to accumulation of charge, so electron holes, and then a circulating current, thermocurrent, will present in the system. The opposite effect is the Peltier effect, as you're saying. So, for instance, the refrigeration mode, we can anchor one part where we have a heat rejection, and by driving a current in this circuit here, thanks to the Peltier effect, we will cool the other side. So Coulomb Peltier are, again, very useful for several many applications where, I mean, you want to avoid any vibration, okay? It's a fully electronic way to cool at substantial temperatures. And these systems here, semiconductor, are indeed very suitable, like other material, because they are intrinsically, can be easily particle-hole asymmetric, okay? So what does it happen in metals? So in metals are known to be poor thermoelectric materials. Why? Because, I mean, their electron hole symmetry is very weak. So they're just is a very modest asymmetry in the system. And one relevant coefficient for all thermoelectricity is the Seebeck coefficient, which basically defines the linear response regime. That means when the temperature difference or temperature gradient is much smaller than the temperature average, the average temperature of the system. Okay, so delta T much smaller than T half, let's say. Okay, so in the linear, this is a typical linear response regime. And so, I mean, if we compare in this graph the Seebeck coefficient in microvolt per Kelvin versus temperature for several elemental metals. Okay, so we see there is tungsten, silver, copper, gold, lead, platinum. So you see, I mean, that you know, around the room temperature, this is of the order at most of the order of microvolt per Kelvin, at room temperature. And then to achieve a sizable or more sizable, let's say, Seebeck effect, we need to go at very large temperature, thousands of Kelvin. So you understand already that, I mean, metals are very poor in the sense of thermoelectricity. And even more if you go at lower temperature, of course, as I will show you. So why? Because, I mean, from the Mott-Jones equation, the Mott-Jones equation states that the Seebeck coefficient, the linear response regime, is just proportional, is a property at the Fermi energy. So it is just set by the ratio of the temperature and the Fermi temperature. Okay, so already you see that this quantity is very small. And this is linear in temperature. The decrease in the temperature, you completely suppress the Seebeck coefficient in the system. So going down in temperature, for instance, in all quantum system or in quantum technology, we would not expect this to increase. I mean, you go down to very small values. Okay, so this is just to say that metals in general are poor, very poor thermoelectric materials. But so, what does it happen? I mean, I am interested in superconductivity. So superconductors are metals typically. So let's say BCS superconductors are metals. So low temperature superconductors are metals. So an important question is, what does it happen if we refer to thermoelectricity in superconductors, okay? So in superconductors, it happens a very interesting things that was put forward by Ginzburg, okay? Ginzburg understood that the thermoelectric, the thermoelectric effect in superconductors manifests in a very sophisticated way, in the sense that if you apply a thermal gradient, let's say, to a bar of superconductor, then of course there will be a thermal gradient in the system, so the quasi-particle will react according to the response of the dissipative fluid in the system, and the opposite, and the system will be shunted by the motion of supercurrent in the system, so the thermoelectricity will appear as a thermophase in a superconductor. So the thermophase is basically the demonstration of thermoelectric response in superconductivity. But what we want, the thermophase is not something good to produce power. to create power in a system, okay? So to manage the energy. So indeed, no thermal voltage, thermoelectric voltage, develops across the superconducting metal. Indeed, thanks to this shunting of the supercurrent inside, which do not prevent the appearing of a voltage drop across the superconductor. And what is interesting, I mean, that the familiar thermoelectric effects which are present in non-metals, I mean, namely the Seebeck and the Peltier, they typically vanish in superconductors. And this stems from the owing nearly perfect electron-hole symmetry, which it does exist in, let's say, conventional superconductor. Of course, I mean, if we look at more specific superconductors like ferromagnetic superconductors or spin-split superconductors, I mean, if there is an external action in order to break the electron-hole symmetry in the system, they will provide a thermoelectric response. But in the absence of, let's say, a wanted, let's say, electron-hole symmetry, they are very symmetric, okay? However, there is an interesting fact, I would say. So 4 years ago, we started to try to understand if it's possible to approach thermoelectricity in quantum systems in a completely different way. So studying nonlinear regime. Nonlinear regime is something, to my mind, that is extremely interesting. So I come from this caloritronic, where you typically impose large thermal gradient in systems, so the systems are driven fully out of equilibrium, okay? And the nature itself is strongly nonlinear. So the question is why we should use the concept of linear response thermoelectricity if the nature in principle is able to provide a much larger response where we are far from equilibrium. So we started to work on this different concept. We understood the following thing. So in the linear regime, as I was saying, thermoelectricity between two conductors indeed is possible in the presence of an explicit breaking of the electron-hole symmetry. So in the linear regime, you have to break electron-hole symmetry in order to provide a suitable thermoelectric response in the system, okay? So if we consider a very basic tunnel junction between metallic electrodes, I mean, we show that this condition is no more required outside the linear regime. So it's possible to demonstrate that, in principle, a thermally biased tunnel junction between two suitable materials can display an absolute negative conductance. So fix this in mind, absolute negative conductance in the system, not differential conductance, absolute negative conductance, and hence the thermoelectric power at finite but small voltage bias, provided the density of state of the electrode is kept and the other is monotonically decreasing. So we can construct, so let's say, reverse the idea of generating power in quantum systems. So to use suitable materials which combine, they are intrinsically electron-hole symmetric, but they are combined in a suitable way that one of the two is just kept and the other has a monotonically decreasing density of states, okay? So if you think to this, we can think to two superconductors. If we make a tunnel junction with two different superconductors, one of them is gapped and the other is monotonically decreasing. No? So we have the tails of the BCS density of states. Okay, so this systems here is the prototypical.
So with one of them you will be within gap and the other one you're going to be outside the gap. That's the idea.
Yeah, so you need just this prototype system. Large gap or a gap. It can be also a bilayer graphene, for instance. You could use also this. And the other is superconducting gap because it's, the BCS is nice because it has the tails that is strongly energy decaying. And this will provide a huge thermoelectric response in the system, as I show you in a short system. So in this system here, when we couple this prototypical system based on two superconductor and basically in the limit of negligible or small Josephson coupling, and I wish to emphasize now that Josephson coupling will be very relevant because it will be like a knob in order to control the amount of thermoelectricity of the system. So like in our heat engine, to have the accelerator that is able to control the power that the engine is able to provide to the system, okay? And
maybe I'm just asking too much in a head.
no.
Then the Josephson coupling is going to come from only one of the leads.
No, from both the leads if you want.
Both of them.
Yeah, I mean, now we are talking about SI prime junction. So this is a fully superconducting junction.
But one is gap, one of the leads is...
Yeah, they are superconductors, two superconductors.
The other one is mono.
Yeah. I mean, the general concept is to have one general gapped system and the other monotonically decreasing. And this holds for if you take two superconductors coupled together. One of the two is gapped and the other, of course, is decreasing. Then there is, of course, the proper choice of the ratio between the two gaps. So what is important is the large gap is hot and the smaller gap is cold. And this reveals the spontaneous breaking of the electron-hole symmetry in the system. Okay, so this is a non-equilibrium induced, basically, spontaneous breaking of electron symmetry in the system, electron-hole symmetry in the system, which gives rise to an enormous thermoelectric response of the system. Okay, so I will show you what is that system. So thermoelectricity in electron-hole symmetric system. So the idea is try to, as I was saying, to give a different vision. So to use combination of quantum materials in order to produce a large thermoelectric response driven by large non-equilibrium. So the sufficient universal condition for finite thermoelectric power, that means that the product of the current and the voltage of the power is less than 0, is negative, is to have a tunnel junction between two particle hole symmetric systems, okay, in the presence of large temperature gradient. So where, as I stressed it again, so the different temperature is of the order of the average temperature. We are strong in non-linear regime in temperature. So very large thermal gradient, okay? This is the point. No linear response regime. And we need that the hot electrode has a gapped density of states, and the cold electrode has a locally monotonically decreasing density of states. This leads to a spontaneous, this can be mathematically demonstrated, that this leads to a spontaneous particle symmetry breaking in the system, okay? So the prototypical example is a tunnel junction between two different superconductors. This is a very well-known system. So we have an S1 insulator S2. S1 is a larger gap residing in T1, hot system. This is a smaller gap superconductor residing at lower temperature. Okay, this is cold. And in this case, so this is a prototypical example of these Josephson junctions, where in principle, I mean, first of all, we suppose that there is no Josephson effect. The Josephson effect will be a dissipationless shunting current in the system, which will allow to control the amount, as I was saying, of thermoelectricity, the power delivered by the Josephson system to the environment, to the rest. So in such sense, to my mind, what is nice is that the idea is to use Josephson systems we typically used, for their intrinsic low dissipation in order to produce power in a system. So to use them as ancillary circuits that, and to manage the energy, for instance, to couple to qubits, there is wasted heat that is collected, for instance, by one of the two electrons, and then we start to recycle this in form of current to produce other mechanisms inside the circuit, okay? So, I mean, if we look at the quasi-particle current in the system, the quasi-particle current is very well-known expression. So in the tunneling mixture, the tunneling expression is just inversely proportional to the resistance of the junction, the tunneling normal state resistance, and the product, the convolution of the density states of the two gaps, and the difference in the frame distribution function. So here we always suppose the system is in quasi-equilibrium, okay? Yes?
Sorry, I don't understand. There is a phase transition associated with this spontaneous particle.
No. No. There is no phase transition. It's just out of equilibrium physics. No phase transition at all. I will show you. Different temperatures. There is no, I mean, they are already BCS.
You can drive the system so that there is the symmetry, and then you can drive to another set of parameters that there is no symmetry, there should be a phase transition.
It's not a phase transition, no. It's just spontaneous electron-hole symmetry breaking. I will show you with the Bogoliubov criterion. I will show you. No, I mean, the two systems are already very symmetric in electron and hole. Is the fact that you are just using this particular combination of shape of density of states, and then you can realize a spontaneous breaking of the electron-hole symmetry. And everything is related to interaction in the system, because, of course, superconductors are strong interacting system, and non-equilibrium physics. But there is no phase transition. I mean, they are already transitioned. Yeah.
So you have a tunneling coupling
between
the two superconductors?
Yes.
And you say that there's going to be only quasi-particle transfer and not
There is also, yes, of course.
No, why of course? I mean, I would like to understand.
Because when you couple two Josephson, when you have a Josephson junction, typically you have also Josephson coupling. You can control this. But thermoelectricity doesn't stem from the Josephson coupling. Stems also only from the quasi-particle contribution.
But what happened with the supercurrent? You are not considering it?
I am considering. I'm just saying that the supercurrent is a superflow, non-dissipative superflow that tends just to shunt the thermoelectric response in the system, similar to what happens by itself in a bare superconductor. But I mean, the thermoelectric response just comes out from the thermoelectric response, just, sorry, I have made, from the quasi-particle current of the system. I'm just saying this. If you write down the expression, the tunnel expression for the quasi-particle current in two different superconductors, different temperatures, in the proper way, where the larger gap is hot and the other is cold, you obtain the manifestation of absolute negative conductance in the system. I will show you. And this is, is the regime of power production, basically, not the power dissipation. So the system starts actively to produce power in your circuit. So it's amazing. It's a property which was completely overlooked, and is something that can be nice to use to produce power in superconducting circuits, as well as to manage energy by using this effect for other more, let's say, developed circuits in some sense. I'll show you. Okay, so as we are saying here, how do we explain this? Well, the picture is very simple. So if we keep in mind how is the energy band description of two superconductors, just here in this image. Okay, so we have a large gap superconductor on the left, a smaller gap superconductor, and then we suppose the large gap superconductor is hot. No? So it is there is more population of electron-like and hole-like excitation in the system. And so you see that when the voltage is equal to 0, there is, they are aligned, the two chemical potentials are aligned, and there is identical contribution of electron-like and hole-like system, because they see the same portion of the tail of the density states. But then if you go, at finite bias, it happens a very remarkable thing, that at near the matching peak, so when the voltage bias of the order of delta 1 T1 minus delta 2 T2, like in this place here, so we shift them, you see that the electron contribution is finite, but there is the hole-like contribution to the current, which tends to diverge because we are matching the two diverging peaks in two structures. And so you see immediately that the resulting current that can be in the system can be dramatically different. So this one is finite, this one can be divergent. So the difference of two is a negative current flowing in the system. So it's absolutely trivial. Okay, so this means that indeed we are using a gap system that is a larger gap superconductor, and the other one has this very nice property of being monotonically decreasing. Okay, in this case, so this is diverging. Here, if it is so this is ideal in this case. So this is why I'm saying that an SIS juncture is really a prototypical system to realize this spontaneous particle symmetry breaking in the system. So this realizing this huge thermoelectric response in the system. Okay, so now if we go more into detail, here we show the current versus voltage of the system. As we are saying, we need two different superconductors. The hot gap is the big gap. The smaller gap is cold. And so look, just is very easily calculated from the tunnel Hamiltonian quasi-particle current. Okay, so you see we start we keep the smaller gap superconductor cold. The larger gap we start heating this. The blue one is the intermediate temperature. You start to see that it develops small negative peaks. Okay, the more interesting here probably is this cyan one, where is an more larger temperature in the system. So you see that it develops a completely negative peak. So the curve maintains its antisymmetry, of course, but in the second and fourth quadrant of the IV characteristic, we have a finite response. So this second and fourth quadrant, these are the way that the junction can produce power in the system, whereas the first and the third are power dissipation in the system. Okay? So if we are able to exploit these two parts here, it means that we are able to exploit the system in order to produce and to make a self-circulating current in the system to produce power in the system. How can we do this? So we need the finite ratio between the two. The finite ratio between a superconductor is between 0.3 and 0.6, let's say. And we need the temperature in the larger gap superconductor is of the order of T2, the second, times delta 1 over delta 2. So high temperature, okay? So we need this to make it really boiling. We need a lot of quasi-particle in the system, as is drawn here. In this case, you develop this fantastic absolute negative conductance. It's not only a differential negative conductance, it's complete absolute, so there is power production in the system here. So we could think that if we close the circuit over a resistor, load resistor, whose characteristic is given by this straight line, when we intersect the two Qs, this for a given load gives us a solution in terms of the proper thermovoltage and proper thermocurrent that will be set in our circuit. So we start to produce like an engine. So the current can circulate in one direction or the other direction. This is why it's very nice, because it's fully bipolar, the system. The system is born in a fully symmetric, electron-hole symmetric, and we obtain, thanks to an equilibrium, a spontaneous breaking of the electron-hole symmetry, but which is fully bipolar. So the current can flow in one direction or the other direction. So this means that we can power energize a fan with the propeller in one direction or the other direction, just by changing if we work here or if we work here. So it's extremely simple. It's a very simple mechanism.
Maybe I can ask a question here, since you have the equation there.
Yeah.
So I see that for the density of the states, you use a Dines.
Yes.
A Dines expression. So how relevant is this if I replace this by some Usadel disorder superconductor or this kind of thing?
Well, it's a good question. I mean, we use this because I am a trivial experimentalist. For me, it's a very phenomenological way to express non-idealities in the junction. So it's true that, I mean, if we consider non-ideal behavior in the junction in terms of partial anti-reflection, I mean, the larger is gamma, let's say, the worse is the response, because it tends to increase the conductance. So it tends to mask this effect here, like the supercurrent itself. This will create a parallel channel, so it will increase the current in the system, okay? So, I mean, and so this is basically what we wish to, first of all, to demonstrate. And you see, I mean, for instance, in this lower part, by changing the ratio of the superconductor for some given temperature gradient between the two, we obtain different behavior. So between 0.3 and 0.6 of the ratio of the capsule, we can obtain the most enhanced effect. If we go over this regime, then we have the conventional, I mean, matching peak that we obtain in conventionally overheated junction. Okay, so there is a specific regime of the two where we can really obtain this this system here. So, yeah, of course.
Do we need superconductivity, or can I do the same thing by having two semiconductors with different band gaps joined together?
So what is important is that, I mean, in principle, you need, as you were saying, one gap, for sure, and then you need a decrease in the second one. Yes. Yeah, but what is important that you need that at the end, this is more sophisticated, is that the Fermi energy pins inside the band gap. Okay? This is crucial. So for a superconductor, this does happen. For a bilayer graphene, this can work. For a charge density wave material, this may happen. So for a periodic insulator, this can happen. So there are some particular way in order that you can combine. Maybe for sure there will be other materials you can do this. Okay. But you need these constraints. Yeah.
So going just 1 second back.
Yeah.
So you do develop some ID power.
Yes.
How symmetric it is on the two leads? Like how much of it is it going more to one direction or the other direction?
Is fully symmetric because the systems are naturally electron-hole symmetric. This is the point.
So if you calculate Q dot,
yeah,
is basically
is identical. So this is completely exactly a bipolar thermoelectricity. This is the point. So this means that your junction, as I was saying, allows current flow in one direction and in the other direction. So you can energize a propeller in one direction or the other direction, for instance. So you can put several of these elements, not like a NP-PN junction, okay? You can put NP, so cold, hot, hot, cold, cold, hot, or whatever, random. They will always give the same response because they're interchangeable, one with respect to the other. So in this sense, it's absolutely different from, let's say, semiconductor thermoelectricity, okay? So as I was saying, we think to combine, for instance, realize a heat engine, no? In this way. So we have a two lateral S prime IS junction, okay, where we have lateral cold superconductor with smaller gap, and the central one is hot superconductor, and then we close this on a load, okay? And this will, I mean, in the presence of this strong non-equilibrium, you see here, this is our cube. This is sigma, is the resistance of our load. I mean, the intersect will set up the solution here in the positive derivative, so because the other one is not a stable solution, only this one is stable. And this will give us, I mean, a circulating current in the system, okay? And so we can exactly, thanks that the system is electron hole symmetric, we can do this, okay? So for let's say, no thermoelectric response is expected in the linear thermoelectric effect in a symmetric structure, okay? So you cannot make NP-PN. NP-PN, they will balance completely, so there is no way to make it this way. So this is says why, I mean, the thermoelectric effect is completely different from so far studied in different systems, okay? So if we study the systems here, for instance, it's possible, I mean, for an aluminum-based structure, aluminum film is the larger gap superconductor, and aluminum copper, for instance, bilayer can be a proximitized bi-invert proximity effect layer to tune the second gap. We can calculate what is expected, okay? Power density versus temperature of the hot electrode and the conductance of the load, and the thermodynamic efficiency. And what is interesting is that the maximum power density for a typical 100 ohm micron square tunnel junction resistance, for instance, that is I mean, quite widespread technology for niobium or aluminum junction, you can achieve maximum power density of the order 0.1 nanowatt per micron square. So this is a huge power. This means that you can easily reach for larger junction from up to 100 nanowatt really in a machine. So this is something that can really produce a large amount of power in a superconducting circuit with a maximum efficiency that is of the order of 40% of the Carnot cycle. So it's pretty high as well. So it's a very efficient thermoelectric machine. And if we look at the Seebeck voltage, for instance, or the Seebeck coefficient, we can achieve, so the Seebeck voltage, Seebeck coefficient, we can achieve something like 200 microvolt, the Seebeck voltage, a coefficient of the order 650 microvolt per Kelvin, which is in this outstanding. So this is a super large. Okay, so this just in theory. Okay, so what is the next step? Next step was to realize experimentally the engine, and we started with the design. So the idea was to use this very simple, a basic old school building block. So everybody knows the quasi-particle tunneling equation, as we have said, the convolution of the density of states times the difference, the Fermi distribution function in the system. Then, to answer to Marcelo, there is the Ambegawa-Baratov equation for the supercurrent in the system. So this is the equation for two different gaps kept at different temperatures, okay? Where we suppose the distribution function to be thermionic, okay? And here, I mean, the equation is the same, just we have the anomalous function for the Cooper pairs, so basically the density of state for the Cooper pairs. Okay, so we have both of them, both contributions, okay? But I was saying, I mean, the pure thermoelectric effect stems only from the quasi-particle contributions. And the Josephson coupling is something more that helps, that is an opportunity in order to tune the device. So how do we tune the Josephson coupling. So the idea was to realize a superconducting quantum interference device, so a SQUID, in order to control the amount of supercurrent in the system. In order to do this very efficiently, we realized a double loop superconducting quantum interference device, because we understood that with a single loop design it was less efficient. So this is a typical design of our, let's say, heat engine. You see we have is a 3-junction SQUID, first junction, second junction, third junction. We have 2 loops, A and B, almost very similar, identical. Then we have a smaller gap superconductor that is a bilayer of copper and aluminum, so to suppress the critical temperature and the gap. Then we have a conventional aluminum superconductor, is the hot superconductor. Okay. Then the system is equipped with several superconducting tunnel junctions, which are used as heater, so to overheat, to make boiling the superconductor here, so the large gap superconductor. And then, so the idea will be to observe the thermoelectric response occurring across this system here in non-equilibrium conditions. Okay. So how do we measure this? So maybe you are expert in this kind of interferometer. These are very particular because what is nice is that thanks to the 2 parameters, phi and phi, they can provide a very large suppression of a very optimal, let's say, suppression of the Josephson coupling in the junction. Okay, much more than a double junction SQUID. This thanks to the fact that this allows more asymmetry in the junction, and you always can find a proper condition where you can really almost suppress the Josephson coupling in the system. Okay. So, at the equilibrium, what do we have? We have no heating. So, everything is the same temperature, no overheating. So, T1 is equal to 2. Then the total flux is the sum of the 2 fluxes. And then we just measure in a 2-terminal configuration. So, we voltage bias the junction. We measure the current flowing in the system, okay, with no heating at the beginning. So, let's see. So, what happens is that, we have the I versus V characteristic of the system, which is is well known from textbooks. So, we see the large onset of quasi-particle tunneling at the sum of the gaps, okay? And then around zero bias, we see the manifestation of Josephson coupling, the violet, and the green curve is for a different flux, which minimizes the Josephson coupling in the system. So you see IC plus, the supercurrent, is positive switching current, the negative switching current, and then for a different flux, you see there is a multiplication by 100, so to see there is a strong suppression thanks to this suitable geometry of the SQUID. Okay, so this is what happens in equilibrium. For what does it happen for the Josephson coupling? So we have studied Josephson coupling in the system, the beating as a function of the flux. You see here, so there is a critical current versus flux fed in the interferometer at different temperatures, so for 30 milli down to 600 milli. And then you see there are some additional bumps here. The bumps comes out when basically the ratio of the lateral junction critical current with respect to the central one is larger than 0.5. So this is something very specific to the design of the interferometer. So it's not so interesting, but just to show you why we have this. And this is just the theoretical behavior expected. So we obtain this just with conservation of the critical current, that is the maximization over the free phase of the interferometer with respect to phi naught, okay, of the sum of 3 current in the system, and then fluxoid quantization in the system. So what is nice that we can obtain always an optimal suppression of the critical current if the interferometer satisfies the triangular relation for that the difference of the ratio of critical current is smaller than 1 and the sum is larger than 1. Okay, so and this may be achieved. So it is on purpose realized very asymmetric in order, that we can satisfy this relation. Indeed, we can achieve a suppression of the order 1.7 parts per 1,000. Okay? This means that we are able to control very nicely a Josephson coupling, so to play later with this in order to control the amount of power that we give to our engine. Now, let's see what does it come out when we talk about full non-equilibrium situations. So now we want to demonstrate bipolar thermoelectricity. So we start keeping the cold electrode at the base temperature of the fridge, 30 milli, and then we start driving power in the large gap superconductor. Okay, so you see We start from 0. The 0 is the blue line, this one. So there is still a small trace of Josephson coupling in the system. And then we start increasing the power. So we start increasing the temperature. You start to see the cyan curve. So, and here we are. Here there is the magic appearance of absolute negative conductance in the system. So this is the manifestation of a spontaneous electron-hole symmetry breaking in the system, thanks to non-equilibrium conditions. You see, negative, positive. So this is power production like this, and this regime here is power dissipation, first and third quadrant, second and fourth, power generation. Then we increase the power, so we increase the temperature gradient. It's a fully nonlinear effect. So you see that increasing the power, we reduce the thermovoltage here, that is a intersect when the current is 0, and the thermocurrent as well. So increasing even more, then we go in a regime where the power production is almost suppressed. It's just power dissipation in the system. So it's very robust effect. The dashed black line is just a fit that we obtain with the equation that I have shown you before, using the sum of the gap at their respective temperature and the difference of the gap as free parameters. Okay, and so you see, the agreement is pretty nice, at least in the rising part. Of course, as you were saying, this part here is more sensitive to quasi-particle states within the gap. So for sure, this is more influenced. But to grasp what is going on, this theory is perfect. It gives exactly what we want. Okay. So from this we can extract another interesting property. So this is our schematized negative absolute conductance. So you see the 2 points fully symmetric. Thanks to bipolar thermoelectricity, they are identical in value of the opposite value. So here you see, that in the junction we can obtain very large thermovoltage that is over the gap. So we have up to 150 microvolt, okay, as a function of the power. And then increasing the power, we reduce basically the thermovoltage in the system. And so conversely, we can define similar way, we can define the nonlinear Seebeck coefficient as the voltage drop, so the thermovoltage divided by the temperature difference between the two. Okay, and this is pretty large, so it can be up to, in our system, 300 microvolt per Kelvin. And what is interesting, that this one monotonically decreases with the temperature gradient, whereas in the linear response regime, the thermoelectric response is always linear in the temperature. Okay, so it is completely different because we are in the nonlinear regime. So we can make just a comparison with the linear Seebeck coefficient for aluminum, but in the normal state from the Mott-Jones equations. So I recall just that. So for aluminum, it's just proportional to the temperature, inversely proportional to the Fermi energy. And for aluminum in the normal state at 600 milli-K, the result is that we have 3.8, around 4 nanovolt per Kelvin. So the response of this artificial system in terms of thermoelectricity is 5 orders of magnitude larger than what you would get for elemental metals. So it's bingo, I'm saying. This means that it's possible, with a wise design of quantum structure to achieve enormous thermoelectric response in your system. So what is the impact of the Josephson effect on thermoelectricity? As we are saying, the Josephson effect is a shunting current, dissipation of shunting current that tends to kill everything, because it tends to rise the negative absolute conductance. So here is just the current in the junction versus voltage for several fluxes imposed across through the interferometer. And so you see that by changing the flux, you can suppress the Josephson coupling. By suppressing Josephson coupling, here are 2 blow-ups, okay, in the positive region, the negative region. They are completely antisymmetric, perfectly antisymmetric. So you see that by changing Josephson coupling, it's like shifting everything up or down. So of course this is nice, because thanks to this you can change the thermovoltage and as well the thermocurrent that the system can provide. So the engine can change the power output for fixed load thanks to the Josephson coupling. So the Josephson coupling will be a phase coherent knob in order to control the response of our engine. So if we plot here the thermovoltage as a function of flux, you see that for different powers, level of power, so different temperature gradient, you see that for low power, there is some tuning of the flux, but at large temperature, the system, being strongly nonlinear, is more sensitive to the flux. So in this, for higher temperature, let's say, difference between the two electrodes, there is more possibility, more fine-tuning of the thermoelectric response, although in a, let's say, in a smaller flux ranges, okay? So as we are saying, this is the, I would say, is the first very simplified version of a Josephson bipolar thermoelectric engine, okay? So since it is fully bipolar, as we are saying, we can, in principle, power our propeller in one direction or the other, in both directions, depending if we are using one volt value or the other value of the thermoelectric system, okay? So how is made the engine to work? Because, I mean, of course, there are some tricks in order to do this. You need a spark. You need a spark in order to ignite your engine. And how is done this? This is performed in this way. So this is the core, the thermoelectric element. We impose a temperature difference thanks to these heaters, okay, quasi-particle heaters in the large gap superconductor. And then we close the circuit with a current bias source, and then we put in parallel a load resistor. Okay, this would be the load resistor where we want to discharge all the power, okay, of the system. So the idea is that it's the following. So we create this thermoelectric effect, nonlinear thermoelectric effect, and in the suitable condition, a current will start to flow. So the current will be the biasing current in parallel with the current flowing in the load itself. So if we measure the voltage drop VL, the power developed in the system on this load will be just VL squared over RL. So there is a straightforward way to measure the power that our Josephson junction can deliver to our load. And how we do this? So this is the schematic, the gray one of our absolute negative conductance curve. And just changing for a fixed load, changing the biasing current means that we are just moving in this way or in the other way, so parallel to this current. So you see that when we start from large currents, at some point we will reach the proper point where we have a solution here. And when we are here for this solution, this means that for this biasing current here that is 0, then the engine is on, and then we have two solutions, that is this or the other. And how do we access to this? So if we start from a positive current, we will move from this part here, and we find this place here. Then we go over, then we switch here, and we go down, boom. Then we go back, and then we will find this solution here, then we switch, and then we go back. So we trace an hysteresis in the IB parameter space. So we can exactly, thanks to the biasing current, decide which is the thermoelectric response, so the sensor rotation of our engine. One part, one sense or the other sense. And this is exactly what I was saying. So by changing the current, we move. So we go down for larger positive current. We are here. Here we have the solution when the current is 0. So this is a spark. It's just to ignite our engine. Then we go over. We continue to increase the current. We switch on this branch here. And here is no more. I mean, there is no more. There is still the finite bias current, but there is no pure thermoelectric response. So if we go back, we design this full hysteresis. So if we look in the voltage drop across the resistor versus a biasing current, I mean, it's just put in the other way. So you see we start from large current. When the current is 0, we have this thermovoltage. It is identical to the -1. And then if we go over, we switch to the state. Then we go back and we switch to the state if we want. But whenever we go to 0, we have a voltage drop that appears here. So when in the suitable condition, indeed, so this means that there is a spontaneous current which is flowing just in our resistor and provides a power dissipated on the resistor. So this is a pure heat engine thanks to the presence of this thermoelectric effect. So this one, sorry, is a pretty large effect. I mean, this I will show you more details. So what is interesting to say is that what can we say about spontaneous symmetry breaking? So there is a very interesting criterion that is called the Bogoliubov criterion for symmetry breaking in quantum systems. Okay, so you see that this is our previous image. So the hysteresis in the V load versus I bias. So we have these two important points. Okay, and this criterion says that if in the thermodynamical limit the solution of the problem do not depend on the direction along which the control variable goes to 0, one has only one phase or solution and no symmetry breaking. But if different solution of the control variable give rise to different limits, 1 and 2, like in our case, one obtains an invariant multiple solution and spontaneous symmetry breaking in the system. So this is a very general criterion, okay? So our super insulator super system under large temperature bias shows hysteresis the biasing current. So this is a manifestation of spontaneous symmetry breaking in the system. So this behavior, I mean, this hysteresis, of course, depends on the degree of non-equilibrium that we impose, or the difference in temperature. So you see that when we increase the temperature, we change the shape of this hysteresis, the width and the height. And eventually, when it's very large, the heating in the system, we lose completely the thermoelectric effect. The only solution is around V equal to 0. Okay, so there is no more thermovoltage, so there is no more current circulating in the load resistor. And here on the right is just the theoretical calculation according to this, just solving very easily the equivalent thermoelectric circuit of this guy here. So conservation of the current and of the voltage drop across the resistor. This gives this solution here. Okay. So what is nice is that with this kind of system, I mean, we can obtain, you immediately see this. This is the prototype of a non-volatile thermoelectric memory cell. So we have two states, depending on where we sit. Okay, so we have one state, 0 state. So thanks to pulses that we give in current pulses, we can use this as a volatile memory cell, so making the system to swap between this state here and this state here. And if you estimate the speed of this junction, it's pretty high because it's just the RC time of the junction. Okay, so it can be several tens of gigahertz. So this could be the first prototype of a thermoelectric memory cell. So how does it behave this? Of course, this is the first ever engine made in this way, so the power is small, okay? And you see, I mean, typically you obtain around some tens of femtowatt because the junctions are very opaque in this case. And this corresponds to 140 nanowatt per square millimeter. But we could easily achieve with the extended Josephson junction some hundreds of nanowatts, let's say, in total. So, of course, the response of the engine depends on the load. So you see, if the load is too low, there is no intersect here. So there is no way to ignite your engine. And then, I mean, changing the slope of the load, of course, there is a different position of the load. So the power as a function, the power delivered to the load as a function of heating, let's say, has a strong dependence on the inkjet power, of course, because it's fully nonlinear. And here you see the general behavior. So by increasing the temperature gradient, it leads to a reduction of the power delivered to the load for different loads. But what is nice is that the power delivered, as I was saying, can be controlled with the flux thread in the interferometer. Okay, so you see that for different loads, you can widen the window where the flux is active. Okay. How does it behave in temperature? So the temperature of the lattice is another important parameter because by increasing the temperature, you increase the electron-phonon coupling in the system with the acoustic phonons in the system. So there is more relaxation with the electron with the lattice phonon. So you see that in general, by changing the lattice temperature, here we fix just the phase across the interferometer. We fix the load. We measure the power dissipation in the resistor as a function of the input power. Okay, and you see that the lower temperature is almost linearly decreasing, and then a sufficiently high temperature. I mean, for fixed power is no more. You are not able to create a sufficient thermal gradient in the system because there is too much coupling with the phonon. So you have to exceed this point where you start to create a non-equilibrium between the two, and then you have this fully non-monotonic behavior. The last one is the behavior as a function of the flux of the power developed across the load for different temperatures away. So you see that by increasing the temperature, at higher temperature, the system, the orange curve, is more prone to be controlled with the flux. Okay, so although in a reduced temperature window. So what is nice is that thanks to this, we can control the thanks to the flux, we can control the power of the engine that delivers to the load. How can we cope with this, let's say, bipolar thermoelectricity? Well, say, I mean, it's absolutely irrelevant if we switch them because it's fully bipolar. So we can put hot, cold, hot, cold, hot, cold, or hot, cold, cold, hot, hot, cold, or completely random. It's not important. I mean, they will completely spontaneously align across the circulating current. So if we want to make large power, we can privilege the total voltage, turbo voltage, just by making a series so that we add all the voltage drop in the system, or just in parallel. Okay, in parallel, I mean, we just privilege the total current in the system, but not the voltage output. But then, I mean, in both of them, we privilege the total power. It is identical. So it's n times the number of the cell that we use in our system. And I wish just to emphasize that the three-junction interferometer that I have shown to you just implements this structure here with three junctions in parallel. Okay? So one could think to use this system for doing more specific things. So my goal would be to use, for instance, this novel thermoelectric element to achieve sufficiently large power, not femtowatts of tens of femtowatts, but let's say nanowatts. And this could be, for instance, creating extended Josephson junctions, and then by controlling within plane fields the Josephson coupling with the Fraunhofer pattern. It would give rise to very large power in the junction. So something that can be useful for something. Okay. For instance, this second example is a microwave-driven thermoelectric memory cell. So I was showing you the first result for the memory cell, but putting this in a coplanar waveguide, this can be driven at sufficiently large frequency. So this can be really a nice way to implement a memory in a superconducting circuit. Also classical circuits, digital circuits. Now the possibility is to implement autonomous electron refrigerators. So what is the autonomous refrigerator? The autonomous refrigerator is a very nice concept in thermodynamics, for which you, it's very nice because it's the concept of cooling by heating. So you heat one part of the circuits, and then thanks to thermodynamics, you cool the other part of the circuits, okay? And here could be the same. So you harvest, say, your hot energy from one part of the circuit, you establish a circulating current due to electricity, and then you use an SNIS, that is a superconducting electron cooler, to cool the electron residing in another part of the circuit. So this could be really the implementation of the autonomous electron refrigerator based on this concept here. Something similar can be done with thermoelectric transistors. So how to tune using interference, control the energy gap in one of the superconductors. So to match exactly the most effective thermoelectric power in the circuit. Another possibility would be, for instance, to realize nonlinear relaxation oscillators. Because these circuits, if you couple this with an inductor, thanks to the RLC, where we have the capacitance, this starts to self-oscillate naturally. And this provides frequency of the order from tens to hundreds of gigahertz, of course, if the superconductor allows you to do this. So this would implement a structure that can be controlled thanks to the flux, so on-chip microwave relaxation oscillator, which are controlled by the flux and eventually also by the load that you put, okay? So in this sense, the next circuit that we are envisioning is the bipolar thermoelectrical superconducting quantum proximity transistor. So what is basically is just a superconducting ring interrupted by a normal superconducting metal. So in a super condition, thanks to the flux, we can control the density of states of this guy here. And then we couple to this guy a hot superconducting electrode. So thanks to this, we can control, the perfect matching of the two delta 1 minus delta 2. So it's an active way to control phase coherently the thermoelectric response of the system. So to realize a phase tunable transistor. For an aluminum-based setup, what is forecast is that you have a max Seebeck coefficient of the order of 400 microvolt per Kelvin, and the thermodynamic efficiency of an engine made its weight of 60%, so super, super large efficiency. And this is something that we could be realized. This is one old design. We did something similar, but not in a context of thermoelectricity, but just for a thermal script that we did with shadow mass evaporation. So by just adapting the structure, we could prove an active tuning of the thermoelectric response of the interferometer, thanks to the proximity effect in the system. Another interesting system is the possibility to realize single photon detector with this. Why? Everybody knows that there are several fields in physics where single photon sensing is very important, and typically most sensor are photon sensor are active. So the advantage of a thermoelectric detector, a TED, is that it's completely passive. So you don't need to energize the circuit. This is the nice thing. So it's just the radiation that shines to your big gap superconductor, and then leads to this non-equilibrium distribution in one of the two, and then the appearance of voltage across your detector. So in this sense, you could realize very large arrays of detectors, completely passive, and then they by themselves energize the system thanks to thermoelectric response. So if you think to realize a system like this, with this mechanism here, in principle, depending on the material, you could work from 15 gigahertz up to 150 petahertz, okay? For instance, with titanium or something based on titanium alloy, you could obtain signal-to-noise ratio for single photon detection of the order of 50 at 50 gigahertz, so in the interesting very low frequency range, typical for axion search, for instance, in dark matter, like WISP. As I was saying, it's fully passive, and then for a given material, the band operation typically can exceed, can be experimented, theoretically demonstrated, can exceed for decades. So this is, in some sense, it can be a promising system. So just to conclude, we have shown the existence of bipolar thermoelectricity in fully particle-hole symmetric superconducting tunnel junctions. So we have used the combination of squid in order to demonstrate the absolute negative conductance in strongly thermally biased interferometers. This gives rise to a thermovoltage and large Seebeck coefficient that is roughly 5 orders of magnitude larger than what is expected in normal matter from the Mod-Jones equation. This system here implements as well the concept of an engine, where we can deliver power of the order of some tens of femtowatt. It's just limited by the tunnel junction transmissivity, let's say, tunnel junction resistance. And at the same time, this implements the prototype of a non-volatile thermoelectric, the first non-volatile Josephson-based thermoelectric memory cell. So here we have some further readings, experimental as well as theoretical. We have produced recently 2 patents on this. One is for this photon detector, and the other for the memory. I don't know if somebody will ever use this, but in any case, we did this stuff. So we enjoy doing these kind of things. And so these are my collaborators that I wish to acknowledge. And at the same time, I thank you for your attention. So I am here. Thanks.
Okay, thanks for the great talk. There is a question here.
Thank you, Francesco. If I well understand, everything is based in the fact that you could apply a gradient between the two parts, right?
Yes.
So how did you, in the experiment, how did you measure that one part is at 600 millikelvin and the other part is, I don't know,